Now, when rings are locked in place like this, we can have something called a stereoisomer occur. Now remember, if we looked at cyclopropane, and here we're looking at cyclopropane with two methyl groups on it. In fact, we could write this out as 1,2-dimethyl cyclopropane. Right? So we have a methyl on the 1 position and the 2 position. Now, if we look at these two different versions where we have one of the methyls pointing up and one of the methyls pointing slightly down versus this position where one is pointing up and the other is pointing up, these two are actually different from each other. And the reason is because we cannot move this methyl from this position to this position or vice versa without actually breaking the ring. And that's because of the intense strain that the ring is on. Remember, I said these hydrogens or any substituent on these carbons can't rotate around. They're not freely rotating, they're fixed in place. So these versions are actually different from each other. They're not the same. In other words, they are isomers, but they're a different kind of isomer. So in this case, we haven't broken a bond, but we have just moved the positioning of the substituents in relation to each other. So isomers, even like this, where we haven't actually changed a bond, but have just changed their positioning, still have different physical properties. Here you can see the isomer on the left has a boiling point of 28.2 degrees Celsius and a melting point of negative 149.6 degrees Celsius, whereas the isomer on the right has a higher boiling point at 37 degrees Celsius and also a higher melting point at negative 140 degrees Celsius. Since these two isomers differ only in their orientation in space, we call them stereoisomers. So stereoisomers are a difference only in space and not in actual bond. So we talked about different types of isomers so far. Constitutional isomers, remember, isomers where they have the same formula, but they're different based on the position of their bonds. Here with a stereoisomer, they have the same formula, they have the same bond positions. Remember, these are both 1,2-dimethyl cyclopropane, but they differ in space. You cannot take these two molecules and orient them in a way to superimpose them where they would look identical. This particular type of stereoisomer, so this is a form of stereoisomer, is called a geometric isomer. And we can describe the differences in them by using the terms cis and trans. So on a di-substituted cycloalkane, like the one we just showed, that contains groups of two different positioning, we can use cis, which means that the isomer has both groups on the same side. So cis is matching, and it means that both groups are on the same side. Or we can use trans to describe that the groups are on opposite sides. Trans meaning opposite or unmatching. These isomers have the same connection. Remember, the bonds are in the same place, but the positioning of the groups in space is different. So again, they are a stereoisomer and a special kind of stereoisomer called a geometric isomer. So if we were to write out the formula for these two rings, in front of the 1,2-dimethylcyclopropane, which we already know how to name, we'd put a description of either cis or trans to describe the relation of the two methyl groups to each other. Again, cis is on the same side of the ring and trans is on the opposite side of the ring. Now for a cis, these could both be pointing up or they could both be pointing down, as long as they're both on the same side. And trans, one always has to be pointing up and one has to be pointing down. Cis and trans isomers are also what we call diastereomers. This is another word to add on, which means that they are not mirror images. So within the type of stereoisomers that exists, we'll get into different types. Enantiomers is another type we'll talk about later, but diastereomer just means not mirror images. And the energies between cis and trans are different. In general, for molecules of these rings that have a cis or a trans, items in the trans position are more stable than those in the cis isomer. And the reason for this is because the cis isomer usually has destabilizing van der Waals interactions, meaning you have interactions between the two groups here. These hydrogens and hydrogens next to each other cause van der Waals interactions that destabilize the molecule. Whereas in this case, where the groups are further apart from each other, you can see there's no interaction and destabilization of the groups overlapping. You could again look at this using a Newman projection and see where you have overlap occurring.